Did you know that you can use really simple mathematics to solve those fancy card tricks magicians perform?
That behind a complicated appearance of every card trick is basic math that performers use to get the outcome that they want?
So pull up a chair and get ready to learn.
Because it's time to explain some math. Welcome to Mathemagic. On this show, we explore the different, interesting, real-world applications of mathematics.
From predicting the weather to navigating satellites, gambling in casinos.
Yeah, or even designing roller coasters, making computer circuits.
Math is everywhere. We couldn't live without it. So we're here to show you the math in our everyday lives and how it works.
Alright, so we were talking about card tricks earlier. Lilia, did you have a trick that you had in mind to show me?
As a matter of fact, I do. You see, my friend showed me this really cool card trick a while ago and I wanted to test it out on you. I think it'll really blow you away. It's called the Final 3 card trick.
Final 3. This sounds really cool. I'm really excited, so amaze me.
Alright, Katie. So pick 3 cards out of the deck. Any 3 cards.
Okay.
Okay, cool. So memorize your 3 cards. Can you show the camera?
I'll show the camera. Okay.
Set out 3 decks. One with 10 cards. 3, 4, 5, 6, 7, 8, 9, 10. One with 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15.
15.
Okay, and then one with another one with 15.
Okay.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And this should have 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, 9. Alright, so put one of your cards on the first deck. Alright, and now cut the second deck any way you want and put it on top of the first deck.
Fancy. I'm gonna cut it.
And then put one of your cards on top of the second deck. Alright, now do the same thing for pile 3.
Just cut it
anywhere you want and then place your card on top of the third deck. Alright, now I'm going to put these 9 remaining cards on top of the third deck and put them on top of each other.
Fancy.
And then I'm going to move the first 4 cards on top of the deck to the bottom. Alright, now I'm going to alternate the cards, putting one face up and one face down, and tell me if you see any of your cards.
I'm not seeing it, guys.
Curious.
You planned this. I'm not supposed to see them.
Alright. Did you see any of your cards?
No, I did not.
Alright, let's try again.
What? Did you do this again? I'm still not gonna see my cards?
Did you see your card?
No, I was watching so intently.
Let's try again.
I hope I'm not like forgetting the cards, but I swear I'm not seeing them.
Alright, let's try one more time.
Are those the 3 cards? Are you kidding me? They seriously are! Dude, look at this! That was so cool! So Lilia, I'm curious about the math behind this card trick. I know most people probably thought she was just splitting the decks at random and somehow coming up with the right cards, but I know that's not the case here.
Well, actually, this trick is purely algebra based. Let's go to the whiteboard and check it out. Let's say that Q is any of your 3 cards. X is any amount of cards you cut in pile 2, and Y is any amount of cards you cut in pile 3. Now let's talk about equations. Initially, the equation for pile 1 would be Q plus 10. But after cutting X cards from the second pile and placing them on top of pile 1, we get X plus Q plus 10. After placing the second Q card on the remainder of pile 2, the equation for pile 2 becomes Q plus 15 minus X. We do the same thing for pile 3. Cut Y cards from pile 3 and place them on pile 2. So now the equation for pile 2 becomes Y plus Q plus 15 minus X. Then we place a third Q card on the remainder of pile 3 so that the equation for pile 3 is Q plus 15 minus Y. Finally, we put the remainder 9 cards on top of pile 3. so that the equation for pile 3 becomes 9 plus q plus 15 minus y. Now let's summarize. So the equation for pile 1 is x plus q plus 10. The equation for pile 2 is y plus q plus 15 minus x. And the equation for pile 3 is 9 plus q plus 15 minus y. We place the third pile on the second pile on the first pile, and then move 4 cards from the top to the bottom, so that the final equation is 5 plus q plus 15 minus y plus q plus 15 minus x plus q plus 14. By rearranging the equation, we can see that cutting x number of cards and y number of cards is just a distraction. It doesn't matter because the x's and y's will cancel out in the end. Because when x minus x is put together, that equals 0, and y minus y put together will equal 0 as well. The only thing that matters is where q is, which is always on an even count. The math magic is presented with facing all even events down. So, after the first run with only 26 cards remaining, we get 7 plus q plus 7 plus q plus 7 plus q plus 2. After the second run with 13 cards left, we get 3 plus q plus 3 plus q plus 3 plus q plus 1. And after the third run with 6 cards left, we get 1 plus q plus 1 plus q plus 1 plus q. And the last run reveals what q plus q plus q.
Wasn't that just so easy? You know, it really was. I was expecting something really hard, but it turned out to be so easy. I had no idea that such simple algebra could be used in complicated card tricks. Well, yes, it can. Alright, cool. Join us next time on Math and Magic, where we debunk the magic in our lives. Have you ever been in a store and ready to check out, but you go to look at all of the lines and they're so long and moving so slowly that you just say to yourself, how do I know which one I'm supposed to get in?
Well, turns out there's a simple way around that. So pull up a chair and get ready to learn.
Because it's time to explain some math. Welcome back to Math and Magic. In this show, we discuss interesting, different, real-world applications of mathematics.
From investigating crime scenes to baking delicious cookies.
To modeling population dynamics or even making music.
Math is everywhere.
Yeah, it is everywhere. And today we're going to talk about something you probably take part in every week at the grocery store. You know, when you go to the grocery store and you're ready to get all of your groceries, you get your bananas, your apples, your mustard, your ketchup, you got that big turkey that you're going to roast for Thanksgiving, and you go to the lines, you're ready to check out, you're going to the checkout lines.
But they're just so long, and they're moving so slow, and you have no idea which one to go into so you can get out the fastest.
Isn't that so scary and just really confusing?
It really is, and I always end up in the line behind the old lady with millions of coupons, and the cashier is super slow, and then she pulls out her checkbook.
Oh, not a checkbook.
A checkbook, I know, I mean, come on, who even has those these days?
Yeah, oh my gosh. But I'm here to tell you that there is a formula that takes the speed of the cashier and the number of people in the line and tells you how fast the line will move.
That's so cool.
Here, we'll go to the whiteboard and we'll show you.
What we're talking about today is called queuing theory. It includes the queuing system, the arrival rate, the occupancy, and the time in the system. The queuing system is a network of people or items that receive services at various points. The arrival rate is the number of arrivals to the queue per unit of time, such as 2 people per minute. The occupancy is the average number of items at a given time, and the time in the system is from entrance to exit for each item. The stability of the queue can be determined with a ratio in Little's law. It states that for a given arrival rate, the time in the system is proportional to the item occupancy, or n equals lambda t, where n is the number of items in the system, lambda is the rate of arrival, and t is the delay per item. Let's see this explained. Imagine that you're going to Disney World, that big, huge, magic kingdom. Think about all of the roller coasters you're going to ride, and those huge Ferris wheels. Consider the amount of money Disney World probably earns every single day, considering the thousands of people who visit it. Let's imagine that every person spends $1 every minute that they're in the park, so the park earns n dollars every minute. Take the previous equation, lambda being the amount of people arriving every minute and t being the time each person spends in the park. This means the rate of park's earnings equals the rate of people's payment. So the number of people multiplied by the time that they spent equals the amount of money the park makes. A queue is stable if the arrival rate is less than the capable capacity of the service point. An unstable system is caused by an overflow of arrivals straining the service and increasing the amount of time each arrival spends in the system. This varying of stability can be seen by burstiness, which happens during those popular hours, such as dinner time for restaurants or outlet malls, which causes interference and inevitably longer delays. But is there a way to make up for it?
Sometimes you just have to wait a longer time at those times of day. However, increasing the efficiency of the service providers can help decrease delays. It's like if you have a really slow cashier and a short line, it's the same as a fast cashier and a long line. How can you use this? Know the times that your store is usually really busy so you can try to avoid those times. Observe the behaviors of the various cashiers working at your store and get a feel for how fast they work. And finally, compare the lengths of the lines with the efficiency of the cashiers to determine how quickly you can get through the line and out the door safe and sound.
That's so cool. I had no idea that you could calculate the efficiency of grocery store lines using such simple math. Next time I'm ready to buy something, I'll know what to do.
Yeah, you really will. Math is all around us, from waiting in grocery store lines to football stadiums to calculating how to go in outer space. Math is always there to help us out.
You're so right, Katie.
Well, that's all we have for today on Mathemagic. We'll see you next time, where we debunk the magic of our lives.